Hello and welcome everyone. So today we'll be learning about chromatin remodelers. In the last class, we had an introduction about what are chromatin remodelers and how they were discovered. So let's do a quick recap about chromatin remodeling complexes. So in vitro studies showed that nucleosome undergoes spontaneous conformational transitions which result in unwrapping of nucleosomal DNA. So for making it possible for unwrapping the nucleosomal DNA, there are two possible mechanisms. One, you can directly alter the DNA histone interactions non-covalently, and other is that you can covalently modify the histone tails or cores. Though the histone tail modifications are more frequent than histone core modifications, so these two possible mechanisms can unwrap the DNA transiently and make it accessible for the transcription factors. Both of these mechanisms required ATP. So chromatin remodeling is done by the help of ATP-dependent nucleosomal remodeling factors. So these remodeling factors modulate the access of transcription factors to the DNA by hydrolyzing ATP. So for hydrolyzing ATP, all those have ATPase domain. Okay, so they can what do remodeling factors do? They can either non-covalently restructure the nucleosome, they can mobilize nucleosome, or they can eject the nucleosome. Okay, so for recruitment of remodeling factors, in the last class we gave an hypothesis for that for recruitment of remodeling factors we need site-specific DNA binding proteins. But in the last class I asked one question, that how are those site-specific DNA binding proteins are able to access the DNA. Yeah, because the DNA is already occluded by nucleosomes, right? So even after occluding by nucleosome, how those remodeling factors can access the DNA. So the possible answers for this are, there are three possible mechanisms. One, nucleosomal breathing. So what happens is nucleosomes are not static. Okay, so nucleosomes are nucleosomes are dynamic. What does dynamic here means? That nucleosome can transiently undergo partial unwrapping. So due to this transient partial unwrapping, some part of DNA is exposed and now it can be accessed by transcription factors. So this mechanism is known as nucleosomal breathing. So this explains that when the DNA gets accessible, then the site-specific DNA binding proteins will bind to that DNA, and then they can recruit remodeling factors. Or the other reason could be interaction with non-coding RNAs or regulatory proteins. So the regulatory proteins have the characteristic that they can bind to histones, and non-coding RNAs are though there are a lot of multiple RNAs which do not code in some proteins. So such RNAs are known as non-coding RNA. These non-coding RNAs can interact with the nucleosomes and they can provide the binding site for the remodeling factors. While the other possible mechanism for recruitment of chromatin remodelers are the pioneer transcription factors. So what are pioneer transcription factors? Are those different from transcription factors? Yes, obviously they are different from transcription factors because they can bind to the nucleosomal DNA as well. Okay, so how do scientists discover that they such kind of things, such transcription factors exist? So what happened was, uh, there is a transcription factor known as FOXA. So this transcription factor was seen that it can bind to normal DNA, the loosened up DNA, as well as nucleosomal DNA. Okay, so how did scientists confirm that the FOXA binds to both kind of DNA? So first they performed chip chromatin immunoprecipitation assay. By doing this assay, they found out the binding sequences of FOXA. Okay, they found out the binding sequence of the FOXA transcription factor. In some other video, I'll explain the chip assay in details. So for now, just get known that if you don't know the chip, you just get known about the fact that it can help you to decipher the sequence to which a certain protein can bind. So here, using chip assays, they found out the binding sequences on the DNA to which FOXA can bind. Okay, so once they found out the binding sequences, DNA binding sequences, they performed EMSA. EMSA is electromobility shift assay. Okay, so what happens that in the gels lab, when you run DNA fragments, they are size sorted. Okay, means the smaller fragment will be seen here while the larger fragment will be seen here, right? You already know about this. So what happens that when those DNA fragments are incubated with protein, which has affinity for DNA, so what will happen? such protein such protein will go and bind to the DNA, so it will form a protein and DNA protein complex, right? So this DNA protein complex, what will happen that assume that you have, okay, just a second, assume that you have a 200 base pair DNA. Okay, and in this DNA there's a certain sequence to which a protein A can bind. Okay, so if you, when those two different DNA fragments, okay, there are two wells, well A and well B. Assume that in well A we put the sample of the DNA, okay, the DNA of 200 base pairs, and in B we put DNA which was incubated with protein. So what is observed that this is the 200 base pair fragment. So when DNA is incubated with protein, the band will be shifted upwards. Okay, so there's a shift in the band. Okay, that's why this types of assays are known as electromobility shift assay. Okay, electrophoretic mobility shift assays. So what scientists said, well, let's get back to our topic, that how by using EMSA they found out that FOXA is pioneer transcription factor, that it can bind to nucleosomal DNA. So what they did was they produced nucleosomal templates. They uh, took different samples. A sample with normal DNA, the loosened up DNA which doesn't have chromatin, the nucleosomal less DNA, and they prepared another sample of nucleosomal DNA. And when they incubated those both DNA samples with FOXA, okay, just for your just take into the consideration that the both samples A and B already has the sequence for FOXA, and how we got to know that, yeah, we used the chip, we deciphered the sequence, we engineered DNA which already has the sequence which can be bound by FOXA. So both A and B has the sequence to which FOXA can bind, and that's why we perform chip assay, right? So both of the samples were incubated with FOXA transcription factors, and then it was run on the gel. Okay, so let's assume there are three wells. This, in the well 1 we put sample X, which is only DNA. Okay, the original DNA, the same DNA that we has taken in the A, but which is not incubated with the FOXA. So let's assume it gives us size X. Okay, so once the normal DNA will bind to FOXA. What will it do? The band will be shifted upwards. Okay, so band will be shifted up. Okay, so band will shifted up in the case of normal DNA. Okay, so the band will be shifted up. So what scientists observe that when they run the sample B is nucleosomal DNA, which is incubated with FOXA. So what should happen? In the normal scenario, this transcription factor shouldn't be able to access the DNA because DNA is already occluded by nucleosomes, right? But what they observed was a same band as of the A sample. So this means that there is same shift in the band. This From this we can conclude that FOXA is binding to the nucleosomal DNA. Which was a surprising fact for the researchers at that time, and thus they separated a category of transcription factors which we call as pioneer transcription factors. And those transcription factors are transcription factors have capability to bind the DNA which is either occluded by nucleosomes or which do not have nucleosomes. So it doesn't matter whether DNA has nucleosomes or not, they can bind to their designated sequences. So binary transcription factors examples are FOXA, SOX2, OCT4. So these are the some examples for the binary transcription factors. So I hope this was clear.